Okay, so now we're just getting started. Please interrupt me if you have any questions about anything or you want me to explain anything more carefully. I'll start with the homework problems that we have on this Google Docs page.
Just getting started.
Oh no, I've got this delay.
About anything or you want me to explain anything.
Okay. So welcome to our new awkward life. This is not actually a very professional studio we're looking at, but okay, so here's the Google Docs page on the different homework problems that I've assigned. And so as you can see, oh no, okay. So here's the Google Docs page, which has the homework. And so as you can see, I'm asking you to put some red marks as several people have done already. And so those are the problems we're going to go through right now. In the meantime, let's switch over then to actually doing some of the problems. Okay. So the first problem is on section 2.7, number 15. And my cat's going to help me out with this. So problem 2.7, number 15, we have the inverse sine of 2t. So can everybody read that right there?
Yeah, I could read it.
Okay, if you can't read it, by the way, you might want to maximize your screen on this one. It should show up on YouTube. I can go check that right now, see if I can see it. Oh, I threw it away, but so since we already have a verification that somebody can see it, I'll assume that we'll be able to find it. Okay. Yeah, so I guess we're doing number 15 first. And my cat's name is Sashka, in case you're curious. Oh, my daughter's cat. Okay, she's not distracting at all. So we're going to do number 15 here, inverse sine of 2t. And so in order to do that, we need to, well, know how to differentiate. And we're just asked to differentiate and find out what's h prime of t. Now, all I'm going to use is the formula. This is just a chain rule. We have the inverse sine function, and then we have the 2t function inside, composed inside of the inverse sine function. So I have a function of a function. So I have to take the derivative of the outside function, leave the inside alone, and then multiply by the derivative of the inside function. And so I need to know how to differentiate the inverse sine. And so we learned that in this section here, is how to differentiate the inverse sine is problem number 19. And so problem number 19 says that, or sorry, formula number 19 says that when I take the inverse sine's derivative, we get 1 over the square root of 1 minus x squared. Okay, so I'm going to use that formula. Inverse sine of x, if I differentiate it, is going to be 1 divided by the square root of 1 minus x squared. Okay, so I need to use that formula if I'm going to do the next problem, which is, so problem number 15, inverse sine of 2t. So to differentiate inverse sine of 2t, well, I have to differentiate the inverse sine. And so I have to do 1 over the square root of 1 minus the input value. But now my input value is not, in this case, x equals 2t. So when I stick in 2t for x, I have to put the 2t squared like that. And then the chain rule says I have to take the derivative of x. And that's just 2 with respect to t. So x prime here is dx dt. And so it's just 2, so I have to take the derivative and then just multiply by 2. So that's the whole answer. And there's not even much to simplify in that one. I could change that to 4t squared. Any questions about that one? Because we're about to do something a little bit worse, a little bit more difficult. And the next one is number 19. And so if we do 19, I guess I can just do it, well, right here underneath. So 19 is sine of t times the inverse cosine of t. And so if I'm going to try to find the derivative of this one, so what rule am I going to use? I'm looking for g prime of t here for number 19. We have the derivative of a product of two different functions, the sine function and the inverse cosine of t. So there's really just a little dot right there. So I'll put a little mark right there. No, not on my iPad. So when I differentiate sine of t times inverse cosine of t, I'm going to use the product rule. So I'm going to differentiate the first one, leave the second one alone. Then I'm going to differentiate the second one and leave the first one alone. And so if I differentiate the first one, it's just derivative of sine is just the cosine of t. And then I leave the second one alone, cosine inverse of t. And then I have to add the derivative, leave the first one alone, sine of t, and now I have to differentiate the second one. So here's the inverse cosine of t, and I have to differentiate that one. So I already differentiated the first one, then I left the second one alone. Now I leave the first one alone and have to differentiate the second one. Okay, so recopy everything. And now the last piece is more complicated. What's the derivative of the inverse cosine of t? Well, same as the derivative of the inverse sine of t was this one. Derivative of the inverse cosine of t is almost the exact same thing, but it has a negative. So it's just negative 1 over 1 minus x squared. And again, that's the formula on the previous page. So just minus 1 divided by square root of 1 minus x squared. Except the x in this case is not an x, the x is a t. So I need a t squared there. Okay, so that's how you do number 19. The next one listed is 20. Okay, well, so right there are natural log of t times e to the t. I actually have no idea what this one is. This is poorly kerned. Kerning is like where you put things in typing. So this could be that we're talking about the function f of t equals the natural log of t times e to the t. Because of the kerning, because there's a space right here between the natural log and the t times e to the t. But order of operations says no. If you don't put the parentheses around it, then that's not correct. It's the natural log of t times e to the t, like that. That's actually what this would be if you entered it into a algebraic computer system, computer algebraic system. So I'm not happy about that one. It could be either way. And if I gave you a problem like that that's ambiguous, either way that you did it, you could argue for it and I'd give you the points. Okay, so that's the one that I'm going to go with because that's how Maple or Mathematica or MATLAB or many other things would interpret that input. Okay, so in this case, again, we have another product rule. and I just have to differentiate the first one, leave the second one alone, then add on, differentiate the second one, and leave the first one alone. So here's your derivative. If I differentiate the first one, derivative of natural log is 1 divided by the argument. And then I leave the second one alone. And now that's the derivative of the first times the second one left alone, plus the derivative of the second one I need to do and leave the first one alone. The derivative of the second one, derivative of e to the t, is just e to the t, and that's it. We're done. Okay. Don't hesitate to speak up if you have any questions about any of these. So the next one, I guess that was number 20. So the next one that somebody wanted was number 24. 24 is a funky one. So the derivative of the sine of the inverse sine of x. Okay, there's a really stupid way to do it, and that's what I'll do because I like to do it the stupid way. But if you were a little more clever, then you just notice that the sine of the inverse sine function, they cancel each other out, and so it is just f of x is really just x. That's all the inverse sine does, is it undoes whatever the sine does, and therefore the sine undoes whatever the inverse sine does. So we just have this inverse sine of x, and then I take the sine of it, I'll just get back x. So that's our function. So here's our derivative, df dx. Again, you could have written it like that. Either way, the same thing. The result is 1. Okay, done. Okay, but you might want to do it the stupid way. Oh, am I supposed to do 21? 21 wasn't check marked, so. Anyway, so let's do it the stupid way for practice in trigonometry. Okay, the stupid way is going to be a nightmare. So alternately, we can take the derivative of the sine of the inverse sine. And so how I do that, so f of x is the sine function of the inverse sine of x. Okay, so we have this outer function and the inner function. So I have a chain rule, a composition of two functions, a function of another function. And so if I want to differentiate it, I'm going to differentiate the outer function and leave the inner function alone. So it's cosine of the inverse sine of x. And then I have to multiply by the derivative of the insert side function that I haven't differentiated yet. And so the derivative of the inverse sine function, again, well, it's right up here, is just 1 divided by the square root of 1 minus x squared. Okay, and we're done. That's the answer. Well, that's not what we got in our first alternate way of doing it. The smarter way, we got 1. So apparently all of this, if they're going to match up, has to simplify down to 1. And it doesn't look promising at all, except that's trigonometry for you. These formulas pop up out of inverse sine functions. And again, the way you look at that is, so this would not be worth full points on a final exam, right? Because that is clearly a way worse input than 1. So how we are going to do this then is, well, you think about it in trigonometry. If I have the inverse sine of x, that means that this, you always think of the inverse sine as the angle. It's the thing that if I take sine of theta, I get x. I know that the sine of theta equals x, and this whole thing is theta. So if I take the sine of the inverse sine, I'm going to get back x. That's what our definition of the inverse sine says. And so if I have the sine of theta equals x, and I draw that on a right triangle, if I have theta here, then if I take the sine of theta, I'm going to get x. Well, the sine of theta is the opposite over the hypotenuse. So given the fact that I can make the scale of this as large or small as I want, I'd say x is here and 1 is here, and that makes sine of theta equals x over 1. So now I'm asking, what's the cosine of theta? Well, the cosine of theta is this.
Greg, could you word up a little bit?
Oh, sorry, thank you. I'm pointing at something you can't see for a long time. Yeah, okay, thank you for correcting that. Okay, how far should I repeat from? I guess I'll repeat the whole thing real quickly. So we're looking at here at the cosine of the inverse sine function. And the inverse sine function, if x is some number, you're thinking of x when we're talking about trigonometric pieces. The x here would be the scalar parts of the sizes of the legs of the triangle. And the inverse sine function will give me the angle that gives me x when I take the sine of it. That's the definition of the inverse sine of x, is that when I take this, it's going to be the theta, it's going to be this angle, that when I take the sine of that angle, I'm going to get x. That's what this means. And so if I now look at this triangle and think of an angle such that when I take the sine of that angle, I'm going to get x. Well, that means I'm going to make the triangle in such a way that this side divided by this side, the opposite side of the angle divided by the hypotenuse of the angle, has to be x. So I'm just going to make it x and 1. I could have made it 10x and 10. So I could make the triangle 10 times bigger if I wanted, and it still works. But regardless, I'm just picking the easiest one of x and 1. And then the idea is, if I know that sine of theta equals x, well, this is theta, and our whole problem here is, what is the cosine of the inverse sine of x? What is this mess? What is this giant monster here? And what it is the cosine of this angle. So the cosine of this angle is right here. That's the cosine of the angle, is this divided by this, the adjacent divided by the hypotenuse. And so the cosine of that angle is going to be, well, I don't know, except Pythagoras knows. Pythagoras knows that this side is going to be this side squared plus this side squared has to be 1. So Pythagoras knows if he solves that equation, then this side has to be the result that when I multiply, add x squared, I'm going to get 1. So the result is the square root of 1 minus x squared. Because if I add this one squared, I'll get 1 minus x squared. Then if I add x squared to 1 minus x squared, I'll get 1. Okay, so I'm doing a bunch of algebra in my head there, because we've done that for a semester in trigonometry before coming to this class. Okay, so the whole result is that the cosine of the inverse sine of x is square root of 1 minus x squared. And therefore, square root of 1 minus x squared divided by square root of 1 minus x squared, this is really equal to 1. And that's it. Okay, that's pretty funky, but that's the sort of trigonometry calculations you do when you do trigonometry with inverse sines. Okay, any questions about that before we move on? Okay, so that was 24. So the next one has more, next section then. We're going on to section 3.1. And I don't know where that is. There we are. Okay, it says we're going to do 3.1, number 13. Oh, okay, well, I don't know if I'm going to need more space. I kind of think I am. I am supposed to look at this problem, which says I am supposed to identify each of the marked points as being an absolute max or a minimum, or relative maximum or a minimum, or neither max, min, relative, or absolute. Okay, and so we're looking at this problem, and they gave us a bit of a graph saying that we're trying to decide whether or not the identified points are maxes or mins, absolute maxes or mins. Yeah, I'm not a big fan of this problem. This one, okay, if we just look at it, so the indicated point here, 2, 1, looks like an absolute minimum. We have this cusp point right here. So when I'm taking the derivative of the 2/3 power of a argument there, The problem is that it has a cusp. It gives you this cusp piece right here, because I'm actually dividing by. Oh, no, actually, it's just that value right there. So it's similar to how the cube or the square root would have a cusp in some sense. The cube root would have some weird spot. This 2/3 power is going to have a problem right there. So the derivative doesn't exist there, but it's still going to have this spot where it's a minimum. At least it's a local minimum. So our big question is, well, does this thing shrink later? Does it get lower? Is it an absolute minimum, or is it just a local minimum? So just the graph indicates that it's a local minimum, at least, and it kind of looks like it's going to be an absolute minimum. One of the problems I have with this thing is that, well, we haven't graphed negative values, so actually it wouldn't necessarily be an absolute minimum, even if it was the smallest over here, because there's other values over here. So that's the question: is, does this have, what's its domain? What numbers can we put into f? Can I actually put in negative numbers in this? Is it okay to put in anything negative? Well, on the bottom, that's okay. I can put in negative numbers and divide by it. Can I put a negative number into the 2/3 power? Well, yeah, it turns out I can take the cube root of positives or negatives, and I can square positives or negatives. So taking the 2/3 power, either one of those operations, the squaring or the cube rooting, is okay. And so I can put in negative numbers. And if I put in negative numbers, however, the top is going to be positive, because when I square it, it becomes positive. Take the cube root of a positive, it's still positive. But the bottom will be negative, so I'm actually going to have negative numbers on the negative x values. So once I get large enough, well, I don't know, maybe the 1 will actually keep it small. No, near x is 0. This is going to be really, really large when I divide by a small number. So near x equals 0, when I divide by something really, really small, it becomes really, really large, but it's going to be negative. So there's going to be a similar asymptote that goes up to infinity from the right. It's going to go down to minus infinity from the left. So it's not an absolute minimum for sure, if you're allowing the domain to be negative numbers also. Okay, so this is a challenging problem just from the idea of, you have to really understand domain and range of this function. You really have to think about what can go in and what can come out. So this thing just looks like a local minimum. And so they also ask about this problem right here, is like, what about this spot right here? Is that a local maximum maybe? It's definitely not an absolute max, because we have these larger values that go off to positive infinity, so it's certainly not an absolute max. So we don't have any max or absolute min in this problem, but we do have local min and maybe a local max if it's the top. So it might be the top if we find that the derivative, see, we can't see very well from this graph. Is it flat there? Did it go up later? Did it go down later? Okay, so we need to analyze this in some way. And so here our calculator is failing to just give us the answer. We actually need to analyze this. We need to do some calculus by hand and figure out what the derivative is. So I'm going to do that on another piece of paper here. Yeah, I doubt I'm going to get all the algebra done in this piece of paper. So let's make a little bit of a mess here. Do the calculus, do the algebra. Okay. Okay, so let's take the derivative here of our f of x and see if I can use up all the paper here, because paper is in scarce quantity right now. It's not easy to find it at the store. So let's see. I want to find f prime of x. And when we find the derivative, we're going to then be able to tell whether or not the function near that spot, well, is the derivative 0? If it's a maximum, the derivative has to be 0. The slope of the tangent line has to be 0 there. And if it's a maximum to the left, the derivative would be positive, because the slope would be going up. And to the right, the derivative would be negative because the slope would be indicating that it would be going down. The function would be going down. So when I take the derivative, I'm going to look to see where the derivative is positive or negative or zero. Okay, and so first you look to see where it's zero. So the derivative of this thing, derivative of 1, is just 0. It's gone. Plus, now we have this mess. Yeah, I'm not excited about it because we're going to have to take the quotient rule and we're going to have to use the chain rule on the top. Well, let's give it a shot. That's why I needed more paper to deal with all the algebra we're going to have to do probably. So I have to do the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. So bottom times derivative of the top. The derivative of the top is that I take the 2/3 exponent, the power down, and I multiply by 2/3. Then I do x minus 2. Then I subtract 1 from the 2/3 is a negative 1/3. And then that would be the derivative of the outside function. Now I have to differentiate the inside function, but it's fortunately just the derivative is 1, so we're finished there. So the derivative of x minus 2 is just 1 minus 0. So the derivative of the inside is nothing. It's trivial. This whole thing is finished. Okay, minus. So still in the quotient rule, I do the bottom times the derivative of the top minus the top, all times the derivative of the bottom. The derivative of the bottom is trivial. It's just 1, all divided by the bottom squared. Okay, so that's the derivative. And I guess I should really simplify it if I could, but I don't really see anything important to do. So I'm looking to see where this derivative, messy as it is, where is the derivative equal to 0? So I'm going to set it equal to 0 to find out whether or not that spot is where I'm going to have a flat spot. Or is it, the picture looks like it's flat from here all the way on. So, okay, I doubt that's true. In reality, there's probably a slight uptick and a slight downtick, or else they wouldn't have asked the question. So one way we could check right now is I could put in the number 1 minus cube root of 2 over 3 in for x here, 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 and here, and see whether or not this all goes to 0. And well, that's one way to do it, or else I can solve this equation to see whether it is where it's equal to 0. So where this function is equal to 0 is where the top is equal to 0. Where the bottom is equal to 0 is not where the derivative is 0. The bottom is equal to 0 where the function is vertical usually, but the function's slope is not going to be defined when the bottom is 0. And for instance, if we just look and see at x equals 0, then the bottom slope is 0, and that means here if x equals 0, our slope is getting vertical. It's getting infinite. Okay, and so that's what's happening as I approach 0 on this one from the left or the right. And there's also this problem where the derivative doesn't exist at 2. When x equals 2, this indicates the derivative doesn't exist. Well, is that true? If x equals 2, does the derivative exist? The derivative is fine here. X equals 2. We have 0 to the 2/3 power, and 0 to the 2/3 power is 0. We're fine. But this one is our problem. When x equals 2, and I put in 2 here, I get 0 to the minus 1/3 power. Now, z to the minus 1/3 power means 1 divided by z to the 1/3 power. The negative exponent means you divide by it algebraically. And so right here I have x minus 2 to the minus 1/3 power means I'm actually dividing by x minus 2. And when x equals 2, that means I'm dividing by 0. So this does not exist when x equals 2. And that's why we have this cusp here, is that I have this problem. The derivative doesn't exist. It's approaching one way from one direction. It's approaching a different value from the other direction. In fact, right here, if you zoomed in on that, I think the graph, like we're not going to see it here, but if you really zoomed in on it properly, the graph would look vertical like that, because the power is, you're dividing by 0, it means the derivative is becoming infinitely large. So that picture doesn't do it justice. The analysis here tells us that no, that picture is wrong. It's not coming in at at some angle. It's coming in vertically like that. Okay, so we're back to trying to find out whether or not this spot is a problem. So, but that is one of the issues, by the way. So when we're doing this problem, you set it equal to 0 and you find the critical values. So the critical values are going to be now, we have a critical value where the derivative doesn't exist. So 0 is one of the critical values. Another one place where it doesn't exist is at 2, where x equals 2. And now a third place where it's a critical value is not just where it doesn't exist here and here, but also when it's equal to 0. And so that's where the top is equal to 0. And so we have to figure out what is what are the spots where it's 0. They gave us a little hint here. They're guessing that the solution is going to be x equals 6, apparently. And x equals 6, then y is going to be 1 plus 6 minus 2 divided by 6. Okay, so if you do all that stuff, you're probably going to get this piece, your output for f. So, but when x equals 6 right here, they said that that's the solution to this up here. So well, let's see how they would come up with that. To set this equal to 0, the next algebra problem is, so now I have this minus this equals 0. I can multiply through by x squared, and I just have this top side equals still 0. So I'm just going to take the top side equals 0, and then I'm going to move this to the other side. So I have 2/3 x times x minus 2 to the minus 1/3 power. I could have put that on the bottom. Minus
Can anyone hear him? Because my volume is down.
No sound. Yeah, there's no sound.
Someone's gonna have to do a play-by-play commentary. Looks like his main camera maybe dropped out. And that's where his voice was being picked up from. Maybe that's why he can't see our messages either. It's totally the cat. We found it out. I took a picture of my homework. I'm not sure if he's going to be able to read it or not. Cool, I'll have to check that out. Looks like your audio is muted still.
Sorry about that. Can everybody hear me now?
Yeah, we can hear you.
Okay, great. Well, I'll just keep going then. Sorry about the technical difficulties.
It's all good, thanks.
Yeah, this is the awkward world we live in for the next couple weeks. Okay, so what we're doing is trying to find the critical number here. The places where the derivative either doesn't exist or has some flat spot, which meaning it's the top or the bottom of a relaxed curve, either the top or the bottom. So we're looking for the maxes or mins. And where its derivative doesn't exist, we found this one to be at x equals 2, was up here. And there's also a place where the derivative doesn't exist at x equals 0. That's where, if I stick it in here, that I have a problem with the derivative. And finally, I'm going to look to see where the derivative is equal to 0. So I set this equal to 0, and I solve the algebra that goes on with trying to find where the derivative is equal to 0. And so the derivative is equal to 0 where the top is equal to 0. And so I just say where that is minus this equals 0. In other words, where that equals this. So where this piece equals this piece is where our derivative is 0. And so now I'm going to put this guy next to this one. Okay, that magically just works out here. We have x minus 2 in the bottom divided by the minus 1/3 power means it's 1 divided by x minus 2 to the 1/3 power, where here z is x minus 2. So if I just multiply both sides by x to the 1/3 power, it will get rid of the denominator here, and it'll put it over here. If I multiply x minus 2 to the 1/3 power by x minus 2 to the 2/3 power, we add the exponents. And so all I'll have is just x minus 2 to the 1 power. And on this side, I'll just have 2/3 x, because I've multiplied by x minus 2 to the 1/3 power. So I've simplified this now quite a bit. So this is where the derivative is 0. In other words, I guess I could move the 2/3 power over here and the 2 over there. If I move the 2 to this side, it becomes positive. If I subtract 2/3 from both sides, I just get 1/3 x. And that tells me that if 1/3 of x is 2, that means x has to be 6. So that's our third critical number, our critical value here. And 0, 2, and 6 are our spots now, where x equals 0 and 2 and 6. And sure enough, that's what we found. 0, 2, and x equals 6, right past 5. Okay, and now I just want to know, to the left, is it positive? And to the right, is it negative? Is the derivative here sloping up and then sloping down? And I could just check that real quickly by putting in a value. The only place that's 0 is at 6. So it's not going to be 0 from 2 to 6. The derivative is not going to be 0. So if I'm looking at f prime of x, I know the derivative does not exist at 2. And then at 6, the derivative is 0. And at 0, it doesn't exist. But here's the only place it's 0, so it's either positive or negative the entire time from here to here. And it's either positive or negative the entire time afterwards. It's never going to be 0 again, so unless it doesn't exist and jumps over, it's going to be always positive or always negative. And so that's the intermediate value theorem again. These theorems are what guide everything we do, but they're hard to test on. So we use them all the time. But I don't really test you on them explicitly. Okay, so I just need to check this question. Is it positive or negative here from 2 to 6? Is this stuff positive or negative from 2 to 6? So I could put in x equals 3. It is a good choice here. If I put in x equals 3 to test, I'll find out whether it's positive or negative, whether the derivative here is positive or negative. And so the derivative is, well, if I x equals 3, I have 3. And here I have 3 minus 2 to the minus 1/3 power. 3 minus 2 is 1, is why I chose x equals 3. I could just sort of see this calculation is going to be easier to make with x equals 3. Because when x equals 3, I have 1 to any power is still just 1. So this whole thing is 1. This whole thing is 1. 3 minus 2 to the 2/3 power again is just 1. So I have a minus 1 on top. And I have a 1 here. And I have x equals 3 is 3 times 2/3 is just 2 times 1. So I have f prime of 3 is just 2 times 1 is 2 minus 1, all divided by 3 squared. So I get positive value. That 2 minus 1 is 1 divided by 9. I don't care what it is. I just cared whether it was positive or negative, and the answer is positive. So, well, that's obvious. The graph actually showed that it was positive. It couldn't be negative anywhere in there because the derivative was 0 here and did not exist here. So it had to be all one value. In order to go positive according to this at all, it had to be positive the entire time. And that's what we've just shown here by checking one value analytically. Okay, it proves what the picture is showing us. The picture is not entirely reliable. I don't really know if that's a max or a min or just a flat spot or anything else. Just looking at the picture doesn't give us the answer. But the mathematics proves it for us so that now when I make my defibrillator work right, according to the algorithm, I know it's going to work. Okay, so after that, I need to find out whether or not the derivative is, what's going on here? Did it get flat here, then did it go up? Or did it get flat here and did it go down? Well, that's the question here. Is the derivative positive or negative for x values greater than 6? So I want to put in a number that's easy to calculate here for the cube root. That's a number greater than 6. And the cube root would be easy to calculate when the whole result is 8. Because 8 to the cube root is 2. Cube root of 8 is 2. So if I put in 10 here, I'm going to check out x equals 10. Right there, and find out whether it's positive or negative there. Because when I put in x equals 10, then I'm going to get 10 minus 2 is 8, and 8 to the cube root is 2. 8 to the negative cube root will be 1/2 then. Okay, so I want to put in x equals 10, and then the result is going to be 10 times 2 is 20 over 3, right here, times 8 to the minus 1/3 power is 1/2, minus Now if I put in 10 here, again, I get 8 to the 2/3 power. Now 8 to the 1/3 power is 2. 8 to the 2/3 power is 2 squared. So I square the cube root. So in other words, I'm going to have 4 for the result of putting 10 minus 2 to the 2/3 power. So you can just calculate that on a calculator or whatever in your head. And finally down here, I'm putting in x equals 10, so I have 10 squared. That's all divided by 10 squared. Now I just want to know, is that greater than 0 or is it less than 0? Now, I don't have to actually do the calculation, but it's pretty easy. Let's see. I have here 20 divided by 2 is 10. 10 thirds is 3 1/3 minus 4 is negative. Okay. So in other words, the derivative here when x equals 10 is negative, so it has to be negative all of the time. Here the derivative is 0, and then it's never 0 again, so it's either positive or negative until well, forever in this case. So that's it, and that's basically the first derivative test, which is what we're going to talk about for the lecture this week. Is the first derivative test says, if I want to find whether or not a function has a maximum or a minimum, at least a local one, a neighborhood max or minimum, then you look to see where the derivative is 0 or does not exist, and that's a critical number. And then you check to see to the left and to the right of the critical number, is the derivative positive to the left and negative to the right, then it's a local max. And so we have positive derivative to the left, negative derivative to the right. So then that says that 6 here, when x equals 6, is local max because the derivative is positive than negative. Derivative is positive means the slope is up, then the derivative is 0, then the derivative is negative, means that I had this positive to 0 to negative, means that the function, the original function, had to be a hill shape. It had to be a local max. Okay, and that's the first derivative test. And so we're halfway done with our lecture for this week that we're going to talk about tomorrow. This was a tough example of that, but it's worth going through all that in detail. Any questions about that before we move on to the next concepts?
No, that's good.
Yep. No questions? Okay. Let's see. That's 13. Oh yeah, and oh, by the way, what is the max? What is the local max? I found that 6 is the max. 6 is the max. I just lied right here. I'm gonna take points off for saying 6 is the max. This is a -1/2. Let me get a red marker here to punish myself, flagellate myself in public. So -1/2 point, because that's bad language. 6 is not the max. Does anybody know what the max is? So 6 is not the max. 6 is where the max occurs. 6 is the x value that you stick into the function to find the maximum. So see, 6 right here is the place where I stick in x equals 6, and then the functions has a maximum there, but the maximum is f of 6. So no, x equals 6 is where the maximum occurs. F of 6 is the max. Okay, that's the maximum value of the function. That's what we're looking for. The maximum value of the function is f of 6. And so I have to stick it back into here. When I stick in f of 6, I get 1 plus 6 minus 2 is 4 to the 2/3 power divided by 6. And when I simplify all that, I'm going to get this 1 plus cube root of 2 divided by 3. If the book is to be believed. Okay, so if the book is to be believed, if they're correct, then this is what f of 6 is, then that should be what it works out to be. Anybody want me to go through that algebra? Yeah, so I guess I have one person on chat saying it. Okay. So just so you know, when people watch this on YouTube, they're not going to be able to follow the chat that's on the Zoom group chat. So it'll be a little bit awkward, but let's see. So how do I calculate f of 6? Let's do that real quick right here. So f of 6, oh, bad marker. F of 6 is going to be that I calculate this function right here that I'm going to put in. F of 6 is 1 plus x minus 2 to the 2/3 power, all divided by x. So I'm putting in 6 in for x, so I just put a 6 minus 2 in here for that one. And so now I just have 1 plus 6 minus 2 is 4 to the 2/3 power, divided by 6. So the arithmetic here, the algebra, is that I have 1 plus 4 to the 2/3 power is just 2 to the 4th power, because it's 2 squared. So 2 squared is 2 to the 4th power. So yeah, 2 to the 4th power to the 3rd power divided by 6. Okay, so it's really, I'm skipping this step where I say 2 squared to the 2/3 power. 2 squared to the 2/3 power is 2 to the 2 times 2/3 is 4/3 divided by 6. Okay, so there's a whole bunch of 2's in here, and there's actually a 2 inside a 6, so I can cancel out one of the 2's. So how many 2's do I have there? What I have here is 2 to the 4th power, means I can take out, that's 2 to the 3/3 times 2 to the 1/3 divided by 2 times 3. So 4/3 is 3/3 plus 1/3. And I took the 3/3 out because that's just 2 to the 1 power. So I took out one of these 2's outside of the cube root. And 2 to the 3/3 is 1 when I divide it by 2. Okay, so these two cancel right there. And so I just have 1 plus 2 to the 1/3 divided by 3, which is exactly what they wrote here. Okay, so that's also what we got here for, let's see, way down here. Okay. So it's always the case that in math, they just skip a lot of steps and they require you to be working your way through them. When you do them in the beginning, you have to do it on paper and you have to carefully do it out. Once you've done that 100 times, you can do it in your head. Once you've done it 1,000 times, you're ready for physics class, because the physicists are much better calculators than the mathematicians. The physicists, the engineers will skip so many more steps and they will leave you in the dust, and they do it for fun. They do it actually for efficiency's sake, but I think they get a little bit of a thrill out of it. So you really, if you want to go on to a scientific career, you're going to want to practice this stuff a lot so you can keep up. Okay, so that's it for that, that problem. That was pretty brutal. I guess I knew it would be. Okay, any questions before we move on? That was 13. So now we have, I'm gonna go a lot faster through 20, 21, 24, and 26, which are, I'm assuming, very similar problems, hopefully not as horrifying. So our next problem is 20 that somebody asked about. Okay, so number 20, I'm going to find the extreme values of this function, f of x equals x squared times the square root of 4 minus x squared. But I'm actually going to limit it to the interval from -2 to 2. Okay, so the problem we're going to have here is that I'm looking for this thing's maximum and minimum values. I'm trying to find where the maxes and mins occur, but I'm only going to rely on the numbers x, which are between -2 and 2. And so that's all we have to look at. And so the critical numbers include always the endpoints of the domain that I give you. So that's the major thing to notice on these ones. That I'm going to take the derivative, set it equal to 0, and find out where the derivative is either 0 or doesn't exist, as in the last time. So where is the derivative 0 or where does the derivative not exist? So I have to take the derivative of this messy function. I'm going to need a product rule and a chain rule. And then I'm going to check where is the derivative 0, where does the derivative not exist? And then I'm also going to have to check the endpoints, because that's automatically a place where the derivative doesn't exist. And it's also a natural place for a max or a min. They almost always occur at those endpoints. Not always. You can make some weird functions where the endpoint is not a max or a min, but 100% of the time, if you're rounding, the endpoints will be maxes or mins. So always look at those spots. Okay, and then we now have to take the derivative of this mess. So another practicing of our problem number 1, sorry, problem number 2 on the midterm, right? So how to take derivatives of these messy functions. So yet another piece of paper. Okay, and I'm looking for the derivative of, I guess I'll put this here, of f of x equals x squared times the square root of 4 minus x squared. So taking this derivative, we're looking on number 20. So the derivative of this thing, the first rule I'm going to use here is product rule, because we have the product is the order of operations here. Then I'm going to have the product of this thing, and the chain rule is later going to happen to this piece. So what we have here is I'm going to have to differentiate the first, leave the second one alone, plus leave the first one alone, differentiate the second one. So the derivative of the first one is 2x, and I leave the second one alone. Oh, I shouldn't have used the square root sign like that. I should use the 1/2 power, right? So in using the product rule, I'm differentiating x squared. Now I'm leaving that one alone. Now I have to add on, leave the first one alone. And now I have to differentiate the second one. And this is 4 minus x squared all to the 1/2 power. Pardon me? Oh, sorry. Good catch. Please start yelling at me faster as soon as you can. Thanks for the catch. Okay, so the product rule here we're doing is differentiate the first one, 2x, leave the second one alone, plus leave the first one alone, and now I have to differentiate the second one. And to differentiate the second one, I'm thinking of that as 4 minus x squared all to the 1/2 power. The 1/2 power means I multiply the 1/2 down. I put the 4 minus x squared in here, and I take 1/2 minus 1, and 1/2 minus 1 is minus 1/2 power. And that's just differentiating the square root function that is outside of all of the 4 minus x squared. So differentiate the square root function of 1/2, leave the inside alone to the minus 1/2 power. I've forgotten now to differentiate the 4 minus x squared. The chain rule says I have to multiply by the derivative of the inside, which is negative 2x. So I need a negative 2x on that one. Okay, that's our derivative, and that's a nightmare if we want to analyze that huge nightmare of a function. Same as last time when we had the 2/3 power nasty function, and especially with a product. So it's a very similar situation. So I don't really want to do it all. I'd fill up this whole sheet and we'd be doing the same calculations as before. So I'm going to let you do that one, the algebra on that. It's very similar. You're going to set this thing equal to 0. and solve for x. And then you're going to get an x value, which if the x value is between -2 and 2, which I expect it is, based on the nature of the function, then you're going to have a critical number where this x gives you the derivative is 0. And then the other piece is that you're going to check when x equals -2. And so then that x becomes a critical number. And that one. And you're also going to have the critical numbers are 2 and x equals -2. Okay, so all those critical numbers are going to be important for solving this problem. So it's a bunch of algebra. And it's the same sort of algebra as before. You're going to move this one to the other side. You're going to multiply it through by 4 minus x squared to the 1/2 power on both sides, because this is in the bottom, really, with the negative exponent. And when I multiply both sides by 4 minus x squared, it would come over to this side and it will eliminate that. Then you're just going to have a quadratic to solve. And so it's very similar to the last one. Okay, and you just don't have the graph to look at it. Okay, so that's number 20. 21. Well, the algebra doesn't look as bad on this one, so I might just do that one all the way through. And then we have 24 and 26. Yeah, I think I'm liking 24 and 21. Okay, I'll do 21 and 24 because this one's very different. It's not algebraic. It's got this trigonometric and exponential function. So first we'll do this algebraic one more algebraic one, and then we'll move on to the transcendental one, which is the e to the x, the exponential, and the trigonometric function. Okay, so I'm going to jump to 21. So this one has a ... an ellipsis. There's more to be done on that one, but I'm not going to finish it. So 21, because it was so similar to the last one. 21, I have f of x equals 3 plus 3 over x on the interval from 1 to 5. So again, we want to take the derivative of this thing. I'm going to then set it equal to 0 to find the critical numbers. And then the other critical numbers are the spots on the endpoints of the domain. Any of the points where we can stick in x's at 1 to 5. Okay, so take its derivative, and the derivative of x plus 3 over x is just 1 plus derivative of 3 over x is 3x to the -1 power. So it's minus 3x to the -2 power. When I differentiate x to the -1, looks like this. X to the -1 power is 3 divided by x here. X to the -1 power just becomes -1 x to the -2. So I get the minus x to the -2. That's it. Nice, cute, simpler one. So I'm happy with doing the algebra on this one. I don't want to draw out the algebra on this one. That's good for your pencil and paper. So now I'm going to set the derivative equal to 0 to find our critical numbers. And so I need to solve for x. So I'll solve for x at this point. I'm going to move this to the other side, and then I'm going to multiply by x squared on both sides to get this 1 divided by x squared out of the denominator there. Okay, so in that case, when I do that algebra that I just said, I get x squared equals 3. So all that simplifies to this with the two operations I just said. First, I move the -3 x to the -2 to the other side, becomes +3 x to the -2. X to the -2, I multiply both sides by x squared, and I get this result. So then that tells me that x equals square root of 3 or minus square root of 3. Okay, so those are my two values here. Now my interval is from 1 to 5, so I throw this one away. I don't care about the -1 anymore. I just care about the positive square root of 3 on the interval from 1 to 5. Okay, so then my critical numbers are x equals 1 is critical, square root of 3 is larger than 1, and 5. Okay, so those are my three critical numbers. Those are the three places where the derivative might not exist at the two endpoints, or it might be 0. I don't know, but they're just special. They're good ones. And then here the derivative is 0. So we found where the derivative is equal to 0, and it was square root of 3. So that's our good chance that it's going to be a flat spot, means it might be the maximum in the middle of increasing, 0, decreasing, or it might be a minimum if it's 0 in between decreasing, 0, and increasing. So the derivative tells us which one it's going to be. I know it's 0 there, so I know it's flat, but to the left, is it positive? If the derivative is positive, good, maybe it's a max, but maybe to the right, the derivative is still positive, so it's not necessarily a max. So I need to check at the right, to the left side, and to the right side. If it's going to be a max, it's going to be positive and then negative. So I need to check this thing right here. I need to check this formula, 1 minus 3x to the minus 2, to the either side of square root of 3. Is this thing positive or is it negative? Is it positive or is it negative to either side of where the derivative is 0? So at x equals the square root of 3, the derivative is 0. So I know it's that. Now, does it go up? Or does the derivative come like this? Or does it do this? Or does it do this? Or does it do this? There's 4 choices here. Positive and negative here, positive and negative here. And so I just need to know which one is it. So I'm going to check some number here to the left of the square root of 3 to see whether it's positive or negative. You know, a good choice, well, I can stick in any number I want into the derivative, except x equals 0. This one is a bad spot. When x equals 0, our derivative doesn't exist. So that's the only bad spot in the whole domain of the real numbers. I can't stick in x equals 0. I couldn't stick it into the function either, though. The function was 3 divided by x. So it's not in the domain of the function or the derivative. But either way, I just need to check some number to the left of the right and of square root of 3. So I'm going to check the number 1 out of curiosity. So I'm just going to check x equals 1 because it's smaller than the square root of 3. It's about right here. And is it positive or negative? And so f prime of 1, well, I put in a 1 here. I get 1 minus 3 times 1 to the minus 2 power, which is just 1. So 1 minus 3 is minus 2. That's negative. Okay, so the answer here was that I get a negative value. So since I have a negative value to the left, I know that the derivative is negative. The derivative being negative means that the function is going down like that. The slope of the function at x equals 1 is negative. It's negative 2 is the value. So the derivative is negative 2. And then as I get closer to the square root of 3, it becomes 0. The derivative is negative, and then it becomes flat. And now I'm wondering what's happening to the right. I'm almost certain it almost always switches to positive value as I switch from negative to positive. Okay. But it's possible that it went from negative to negative. It could go negative, flat, and negative. Algebra allows that possibility. So I also have to check here x equals something bigger than square root of 3, like x equals 2 is fine. Any number bigger. Oh, I guess I'd kind of like 5. That's a better choice here. I'd like to know what's happening at the endpoint. So yeah, let's not do x equals 2. Let's do x equals 5 is our next place to check. But 2 would have been fine. It would have told us the answer. It would have told us the answer at 5 also. Whatever, it doesn't matter which one you pick. So x equals 5, I'm going to check that. And so f prime of 5 is, well, 1 minus 3 divided by 5 squared. So x to the minus 2 power means that I put in 5 to the minus 2 is 5 squared in the bottom, which is just 25. Now 1 minus 3 over 25, is that positive or is it negative? That's our question. That's all I care about. I don't care what the actual value is. I just want to know, is it positive or is it negative? And in this case, 1 minus a fraction smaller than 1 is going to be positive. So it's greater than 0. So I'm again going to see that it's positive there. So I found that my derivative is at 0 at this critical number where we solved where it's 0. And now I've checked that my derivative, well, this is the only place it's 0. So it's not going to be 0 anywhere else. So it's always going to be negative from here until it doesn't exist or it hits another 0. So all the way from here to here, it's going to be all negative or all positive. And we decided it's all negative. Then after here, there's no other critical numbers. So again, there's no other place where I could switch from positive to negative or negative to positive. So I check at one spot, it's positive. I check that x equals 5. It's positive at x equals 5. At that spot, it's positive. So it's positive everywhere, all the way through there. Again, that's the intermediate value theorem that guarantees that's not going to switch. The only way I could switch from positive to negative is either it doesn't exist and jumps, or else if it goes through the x-axis and it goes through where the derivative is 0. So it doesn't. So we have that it had to be negative all the way from here to here and positive all the way from here to here, the derivative. Now the derivative being negative doesn't mean that the original function f of x is negative. The original function f of x, if its derivative is negative, it means the original function has a slope that's negative. If the original function's slope is negative, that means the function is decreasing from there to there. So throughout this interval, I know the function is decreasing and then it hits 0 there. So the slope looks like this. It's negative, then it's 0. And then afterwards it switches to positive. So it's negative, 0, positive. So it's going to look like that. And so because of this, therefore, the first derivative test guarantees that f has a max or a min at x equals the critical number square root of 3. So the first derivative test is checking that the first derivative is negative here, then positive here. So it's negative, then it's 0, then it's positive. So the first derivative test says that f has a minimum at x equals square root of 3 because it has that shape for its graph. So that's what we're looking at. And that's what we've solved here with our analysis. This is the analysis of it, and where we just did all this by hand. So again, the computer would do a different approach usually to figure that out. So we have a minimum at x equals root 3 and a minimum. What is f's minimum? The minimum is at x equals square root of 3. The minimum is f of square root of 3. So I have to stick the square root of 3 back into the original function. Now, not into the derivative. The derivative is telling us whether its slope value is. And if I put in square root of 3 into the derivative, I'm going to get 0. That's how we found it. But I have to put it back into the original function to find out what's the minimum of this function. And so it's a local minimum, by the way, as far as we know. And because that's all we've checked. The first derivative test doesn't tell you if it's a global max or global min. So let's check that in a second. And so when I stick in x equals square root of 3, I'm just going to get f of 3 here. F of the square root of 3 is square root of 3 plus 3 divided by the square root of 3. Okay, not much to simplify there. I don't care much about that. We could factor out a square root of 3 and then it would just be messier. So it's fine. You could simplify it a little bit if you were an engineer by giving me a decimal answer. But to a mathematician, that's the superior answer. That's the perfect answer. Okay, so that's our local minimum. Is it a global min? I don't know yet. But the way you figure out whether it's a global min is just to list all the possibilities. you put in your x's, you find out what your f of x's are. And so all the critical numbers here, I put in for my x's. And those are the only possible places to have minimums, whether they're local or
Can you
global.
move it up, please?
Oh, thank you. Okay, so I'm going to stick in all my critical numbers here that we've found. And the critical numbers that we found, well, all I found was square root of 3. That's the only thing we've found so far. And so the only other issue is that we're looking on the interval from 1 to 5. So the other critical values are 1 and 5. So that's the only possibilities for local maxes, local mins, or global maxes or global mins. And so if I just figure them all out, those are the only possibilities. And so what's f of 1? F of 1 is, let's see, this whole thing collapsed again. Looking for 21. Oh, I lost my problem. Wow. Okay. I don't know where we're at. Anybody help me out with the page number that we're going for on this? Hmm.
135.
135. Thank you.
36.
Uh, 136. Okay. I don't know what happened. I jumped. I think I hit the bottom accidentally. Okay, so we're looking at page 136 on problem number 21. And so we're looking at this problem. I'm trying to find out where is f of x a max or a min. And so I'm going to stick in my critical numbers, which are the endpoints 1 and 5. And then the place where we found the derivative was 0 at x equals square root of 3. And so that's where the derivative is 0, or on the endpoints, the derivative technically doesn't exist. So I stick in x to the original function f, and I'm going to get 1 plus 3 divided by 1 is 4. Square root of 3 gave me this value, root 3 plus 3 over root 3. 3 over root 3 is actually just root 3, or there's a lot of simplification that I can do then. See, 3 over the square root of 3, they talk about rationalizing the denominator. It's really just, well, I don't know, there's lots of ways to do it, but 3 is the square root of 3 squared, and square root of 3 on the bottom just means that this whole thing is really just simplifies to square root of 3. So 3 over the square root of 3 is just square root of 3. So this whole thing is just 2 times the square root of 3. 5 minutes ago, I told you I couldn't simplify that at all. And so yet another example of me lying to you. You can't trust anybody, including yourself. When you do math, you make lots of mistakes. It's a good thing to be comfortable and relaxed with making mistakes in math. Don't judge yourself about it. Just keep going. Okay, so f of square root of 3 is 2 square root of 3. Square root of 3 is around 1.7. So this whole thing is 2 times 1.7. So we're at 3.4. It's still smaller than 4. So this one's smaller than this one. So this one's the leading contender now for the max right now. But I'm going to also stick in x equals 5. And when I do that, I get 5 plus 3/5. And that's 5.6 then. 3/5 is 6/10. Okay, so I got 4, I got 5.6, and I got around 1.4. No, sorry, 1.7 squared. Okay, it's 3. So this is the smallest. So this is the absolute min. This one's not an absolute min, but this is the absolute max. So this is the absolute max. This is the absolute min. And so now we want to wonder, what is this thing? Well, it's a local something. Is it a local max or is it a local min? Well, so it's local something. And if I check at x equals 1 up here, I know that the derivative is negative at that spot. So the derivative is negative, and it's smaller than this one, so it's a local min? No. Okay, that's me just trying to confuse you, as if math wasn't confusing enough. When the derivative is negative, it doesn't necessarily mean it's a min. See, on the left side, f of x at x equals 1, I have f of 1 is 4. So at 4, then the derivative is negative, means it's going down there. So because on the left endpoint, the derivative is negative, it means it's a local max. At x equals 1. Then we got to x equals root 3, and their answer here was 1 point something. It gave me this local min that we found. First derivative test guaranteed that f has a minimum at root 3 of f of root 3. So at x equals root 3, we had derivative was 0. To the left, the derivative was negative, and to the right, the derivative is positive, so it's going to be going up. So this is what the function is going to look like roughly. This is what f is going to look like. The derivative goes negative, so the function's decreasing. Derivative is 0, so the function is flat. Derivative is positive, so the function is increasing. And then when x equals 5, over here, we got 5.6.
Can you move it up again, please?
Oh, yep. Oh, yikes. Yeah, okay. I've been talking for 2 minutes. Thanks for the help. Okay, so to repeat everything that I've been talking about, the derivative is 0. That's way up there, okay. Derivative is 0 at root 3, derivative is negative here, derivative is positive over here. So the function itself looks like decreasing, then flat, then increasing. Okay, and when x equals 1, at that endpoint, when x equals 1, I have a 4 value for my f, and the derivative at that spot is negative. So it means it's decreasing there, which means that f is a local maximum. Sorry, f has a local maximum at x equals 1. So here's the x values at 1, root 3, and 5. And the function is going to look something like this, that the function is 4, then it's 2 root 3, and then it's 5.6. So it's going to decrease to increase. Again, that's the first derivative test that guarantees that f has a minimum at this spot because the derivative we found was negative here. The derivative is negative means the function is decreasing. We found the derivative is negative. And then the first derivative test also checks on the other side, the derivative is positive. That means the function is increasing. The slope is positive. Okay, so that's it. Again, not a nutshell. That was a long, complicated explanation. But it also means you want to be careful about your endpoint maxes and mins, as well as your critical numbers inside where the derivative is 0 or doesn't exist. Any other questions about that whole thing? Okay. Well, go ahead and interrupt me if you think of anything. But aside from that, I'll go on to this one. And this, in some sense, serves for the lecture for this week too. I'm forecasting into the next section, which is about finding using the first derivative test. So that's what I'm doing right now. Okay, and so if I look here, I want to now take the derivative of e to the x times the sine of x, and I'm going to do the exact same thing. So I'm going to repeat everything. I'm going to take the derivative of the function. I'll get a different, messier answer. I'm going to look on the limited endpoints, so from 0 to pi instead of from 1 to 5. And I'm going to find where the derivative is 0 inside. There's no place where the derivative doesn't exist. This is a fine function. So I won't get any breaks. I won't get any jumps. So I'm just going to have to check 0, pi, and wherever it's the derivative is 0 inside that interval. Okay, I just want to do this one quickly because I'm going to do the exact same thing of everything, but I'm not going to do all this stuff. All I'm going to do is do the algebra to see what happens on this one. The algebra on this one is just that I need to solve an equation that has sine function and e to the x in it. So that's the extra twist on this one. So let's do that quickly. All I'm going to do is this first two lines of this one, which had easy algebra of when the derivative was this easy algebraic equation, then the solution was instant. Well, now with e to the x sine of x, maybe the solution is going to be a different way of thinking at least. So I'm just doing these two top lines. I'm going to not do all this extra analysis of the first derivative test, but you would do that. You would calculate whether the derivative is positive or negative to either side, and you check this exact same thing. So this is the really important spot right here to me. This sums it up. This picture tells me where the derivative is 0, and then you just check, is it positive or negative between the spots where it's 0. And that tells you everything there is to know thanks to the first derivative test, whether it's decreasing to flat to increasing or vice versa. Okay, so okay, did I somehow do it again? No. All right. So here's our function, e to the x times sine of x. So again, I'm going to use a product rule on this one. So when I differentiate this mess, I need to differentiate the first one, leave the second one alone, plus I'm going to leave the first one alone and then differentiate the second one. Okay, this is a little confusing because when I differentiate the first one, well, nothing happens to e to the x. It's the function whose derivative is itself. Now I don't touch the second one. Plus, now I leave the first one alone and I differentiate the second one. And that's our derivative. So we've used the product rule on that thing. Again, for trying to find maxes and mins on this interval, I'm going to find the critical numbers by setting that equal to 0 and solve for x. Okay, when I solve for x, I'm going to now, I don't know. Well, one thing I know is that e to the x times e to the x itself is never 0. Okay, e to the x, its graph is just always above the x-axis. And so this part's never 0. I don't have to worry about that one in some sense. I can factor out the e to the x and then divide both sides by e to the x. And I just have sine of x equals the cosine of x. So that equation is the same thing. That's equivalent to this simpler equation, just dividing both sides by e to the x. Because 0 divided by anything is 0, except 0. Okay. So now I need to know, where is the sine function equal to the cosine function? Well, that's not a solvable thing, okay? I can't figure out. Where is the sine function equal to the cosine function? So this one's a sine function, and the cosine function is the same sort of function, but it's 0 when these ones are, they have the opposite of their maxes and mins, and they're zeros. Okay, so cosine function is the one that starts at 1. Sine function starts at 0. And I'm wondering, where is sine of x equal to cosine of x? Well, there it is. That's where sine equals cosine. And there it is. Okay, those are two spots. And then there's going to be infinitely many more places where they cross each other as we move all the way through. Now, I don't really care about all the infinite places where they're equal. That's where they're 0. I only care about them from 0 to pi. So from 0 to pi is from here to here. So that's pi right there, is where the sine function goes from 0 at 0. At pi over 2, it's maximum. And then at pi, it's 0 again. So the only place where the cosine function equals the sine function is right there on the limited spot that we care about, from 0 to pi. So it's right there. Okay, and that's where the sine function equals the cosine function. So this is a difficult question that I won't be sticking this to you on the quiz or on the midterm. I want you to see it in the homework because you're going to see it in life. Okay, in real life, you won't be able to solve most problems. You're going to need to use some numerical technique, which means you're going to have to use a calculator, which means you're going to have to use a computer to solve the math problems, because real life is not a cute little math class where the math teacher chooses an easy problem to solve that's going to come out easy in the beginning. So this is a bad one. This is a rough one. I don't know how to algebraically solve this. Nobody does. Here we go. If I was going to try to solve this, so this is going to fail. And, you know, I'm comfortable with that. Being a mathematician is about making mistake, 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 and just keeping confident that, well, it's worth the attempt. So here's a crappy attempt. I could take the inverse sine of both sides. If I take the inverse sine of both sides, I just get x equals the inverse sine of the cosine of x. Okay, I'm trying to solve for x, and there's x. Well, but x is solved in terms of x itself. So I haven't isolated x. I want x on one side. I want to know what x is as a number. I want to get all the x's on one side and simplify it. And there's no formula for doing that with the elementary functions. You just don't get anywhere. So you need to rely on numerical techniques. And so that's not about this class so much. Okay, so you're going to do a more numerical analysis type class. You're going to deal with that in computer science, and you're going to deal with that in Math 420. Numerical analysis is what it's called. When you're going to break down and try to find, well, what is that number? I know it's less than pi over 2, which is 1.57 approximately. So it looks to me like it's around 0.6 or something like that. Okay, and so there's techniques in every computer system. It's in your calculator for finding, how do I solve an equation that I can't algebraically figure out, that I can't analytically just solve it by hand. So you're going to need to have an algorithm to do that. And so again, I'm not worrying about it too much. I'm just bringing it up with this problem. So this thing, use your calculator, because this thing failed. I couldn't algebraically solve it. So use your calculator to approximate the answer. I don't know if it's 0.6. I have no clue. Okay, I don't have a calculator here, even though I'm sitting here with 4 computers in order to live stream this. Okay, so you find your approximate value, and that's what it's looking like, and then that's your critical number, about 0.6. And so you're also going to be interested in 0, pi, and your critical number, which your critical number is now only going to be approximate. You're not going to get the perfect answer. Last time where we got square root of 3 is the perfect answer to all decimal place accuracy. Okay, so any questions about that? It is worth struggling with these sometimes. You know, a lot of problems in math don't lend themselves to analytical solutions. It's just the problem is analytical, but the solution is not. We don't know what the result is. But I do know the result exists. Again, that's what the theory is about. So how do I know that the problem has a solution at all? Again, that's the intermediate value theorem. Again, that theory is what gives us confidence to keep moving. And the idea is that it went from sine of x. Wait. I'm sorry. When I simplified this, I didn't do a negative. So I have sine of x plus cosine of x equals 0. I should have had sine of x equals minus cosine of x. So all this stuff is wrong. That's life. Again, failing, keep going, figuring out what you made a mistake about is good. So not genuinely apologizing, but it's everything else I said about it with just a minus up here is still valid. Okay, so that's all I want to say about that one. Use your calculator to get an approximate answer, and then keep doing the analysis. You check to see whether the derivative is positive or negative on either side to see whether or not this value of, now I really don't know which number it is going to be a max or a min. And then check your endpoints. Okay, so moving on. That was 24. Last one is 26. And I said I didn't really want to do it. So again, because 26 here is an algebraic one, very similar to the other ones. So give those a shot, give them a try. I've been going for 38 minutes longer than I normally would because this is so awkward. But give that a shot. If you don't understand it, then Zoom me and we can do it in person. And we can go through it where you can show me what you did, and I'll tell you where you got something wrong. But it's the same process as the first two algebraic ones we did. Okay, so that's it for today's discussion of how to do the homework. That's what I'm going to be doing every week on Tuesdays, and I'll be uploading it to YouTube in case you can't make it at this time. Some people work, that sort of thing. And so, but if you have any further questions, please email me, and we can set up a Zoom at any time. Aside from that, that's it. I'm going to cancel the video, but I'll stick around for a little bit if anybody wants to speak to me personally. Thank you very much, everyone.
Yeah, thank you.
Oh, somebody just emailed or chatted, when's the lecture? The lecture is tomorrow on Wednesdays, every week on Wednesdays at 2 o'clock. I'll do the lecture, and we'll just be covering this same sort of thing. Okay, so see you again tomorrow, and I'll sign off.
Yep, bye.
Bye.